My name is Mohammad Haq. I am a postdoctoral researcher at the University of Helsinki. I'm presenting a work titled The Bits of Silence, Genuine Traffic in VoIP. Silence is a fundamental characteristic of speech. Indeed, human conversations are characterized by brief pauses and so-called turn-taking behavior. In the top figure, we notice that there are brief pauses when a speaker, Alice, talks to Bob and Bob listens. Therefore, there are long pauses for Bob as well. The duration of such events may vary from a few hundred milliseconds to seconds. In the context of VoIP, this means that there are frequent periods where the microphone only captures background noise. This can result in significant processing and communication overhead, as the corresponding packets do not carry useful information. During congestion and natural disaster, the networking resources are very limited. Note that our conversations can take place at home or office or even in the subway. These different places have different noise characteristics, which may affect our conversation at the other end. Therefore, we perform experiments considering the conversation context while conversations take place. There were noiseless conversations, conversations with moderate noise, and conversations with extreme noise. The first two contexts represent typical indoor contexts, and the last one emulates the noisiest outdoor context. We first initiate VoIP calls between two devices in a noise-reduced room. The average sound level in the room was 34 dBA. The devices of the both call participants are placed in the same room and exposed to the recorded speech according to the figure. In the urban settings, we are exposed to more sound in indoor public places or outdoor. For example, in NYC, people experience a mean sound level of 75 and 74 dBA due to pedestrian and transport traffic. A community gathering in a living room can create a sound level of 55 dBA. In order to add such noise to the conversation, we used another laptop playing recorded audio in a coffee shop and kindergarten playground. This is also explained in this figure. In this work, we investigate the performance of Skype, WhatsApp, Duo, Viber, and Facebook Messenger. In order to understand the performance of these applications during silent turns, we experiment them in a silent room. We used a Nexus 6 and an iPhone 6. After initiating calls, both participants are silent in the room. In the table, we notice that WhatsApp, Viber, and Facebook have the lower bit rates than Skype and Duo. This indicates that these three applications may suppress silence during conversation. In the next set of experiments, the actual conversation takes place in the silent room. In the bottom figure shows that the bit rates of these applications synchronized with the speech signals. And we noticed that the bitrate of Viber, WhatsApp, and Facebook Messenger actually fluctuate according to the speech signal, and their minimum bit rates can be zero during the silent turns, whereas Duo and Skype always have the maximum bit rates. Although we have seen that there are pauses in data transmission of the applications due to silent turns or pauses, all the applications do not have similar performance. In the absence of noise, Facebook Messenger and Viber suppress 21 and 30 seconds of silence from conversation. WhatsApp, on the other hand, uses lower bitrates but doesn't suppress traffic completely. However, the bitrates of Facebook Messenger and Viber increase as the surrounding noise increases. In contrast, Skype and Duo do not perform any silence suppression. These two applications do not react to noise as well, and they always have very high constant bit rates. Next, we investigate the flow properties such as the interpacket gaps and packet size distribution to shed light on how the codecs of these applications perform silence suppression and deal with the noise. These plots compare the distributions of interpacket gaps during conversations. WhatsApp uses a constant packet gap of 60 milliseconds. The packet gaps of other applications decrease when the actual conversation takes place or the surrounding noise increases. In the case of Duo, the distribution remains the same irrespective of the conversation or the noise context. Next, we investigate the distributions of packet size of these applications. These plots compare the distributions of packet size. In general, the applications use larger packets when the actual conversations take place. The distributions of packet size vary as the context becomes noisier, specifically Viber and WhatsApp. WhatsApp and Viber have the smallest packets, whereas the Facebook Messenger generate the largest packets for conversations. Our findings during one-to-one conversations reveal that only a few applications actually suppress silence. Facebook Messenger and Viber can suppress traffic for 75% and 39% of total silent periods. Uh, with moderate noise in the room, their achievements actually reduced to 48% and 30% respectively. Therefore, these applications actually exchange more traffic with the noisier context, and the overhead is quite significant as shown in this figure. Although both iPhone 6 and Nexus 6 perform silent suppression, we experienced relatively more data from iPhone 6 compared to Nexus 6. However, the performance of the applications didn't vary as the network changes from LTE to Wi-Fi. Connecting earbuds with the devices during conversations didn't affect the traffic pattern either. Finally, from the flows or traffic flow properties, we have identified that Duo uses G.711 and Skype uses CELT. These two are constant bitrate codecs. In contrast, WhatsApp uses Silk, Facebook Messenger uses ISAC, and Fiverr uses IPMR. All these are variable bitrate codecs. Therefore, these applications suppress silence by taking advantage of dynamic transmission rates or switching to a discontinuous transmission mode. Nevertheless, silent turns are more prevalent in multi-party or group conversations, as the turn-taking time may increase with the number of participants. Therefore, we also investigated the performance of these VoIP applications with multiple participants, except Duo. The host and the participants are in two separate rooms. We performed two sets of experiments. In the first set, when the host speaks and others listen in a silent room. In the second experiment, the host speaks and the others mute their microphones, as it is more common to mute mics during group conversations. There were four participants in group conversations. As mentioned earlier, that we had two sets of group conversations. In a normal conversation, a participant receives aggregated data from all the participants. In the case of muted conversation, all the participants generate very small traffic, even Skype, which is smaller than the silent traffic. However, the participants receive burst traffic from the Skype server. As the number of participants decreases, the number of bursts decreases. And the aggregated bitrate is the sum of muted traffic from all other individual participants. Viber, on the other hand, drops the muted packets at the server. The muted traffic from WhatsApp and Facebook Messenger is also aggregated. However, the traffic pattern is continuous. Therefore, the results suggest that actually Skype and Viber may not be true peer-to-peer during group conversations. They also look into the traffic pattern to identify whether the packet is carrying actual voice data or not. Earlier, we investigated the performance of the VoIP applications in consuming data while dealing with silence and noise. Now we look into the LT physical layer resource consumption. We used the network signal guru application on Nexus 6 to capture the physical layer properties of LTE during the VoIP conversations. In this figure, we notice that lower modulation takes place for muted conversations, and only four physical resource blocks are allocated, except Duo. As we have seen that Duo exchanges more traffic even when the microphone is muted. In the presence of conversation and noise, higher modulation scheme is prevalent. Facebook Messenger uses the higher resource blocks and lower modulation. Another exception is Viber, which uses smaller packets and use lower modulation and smaller resource blocks. These VoIP applications may consume significant energy during the silence periods, conversations, or even when the microphone is muted. We developed a simple energy profiling tool that only measures current drop Nexus 6 at 2 Hz. In these figures, we notice that Facebook is 50 to 200% more energy efficient than the other applications. Skype and WhatsApp perform similarly, even though Skype has very higher bit rates than and WhatsApp. Interestingly, Viber consumes more energy than Skype and WhatsApp, even though it suppresses traffic for the silence periods. This behavior was consistent across multiple measurements, and we believe that the codec is the likely reason. In general, these applications more energy as the context becomes noisier. We further compared the performance of the VoIP applications with the VoLTE calls. In this figure, we notice that VoLTE uses the wideband codec AMRWB. The bitrate varies between 7.6 to 18 kilobits per second, and mostly 4 resource blocks are allocated during the conversations. This indicates that this wideband codec also uses smaller packets like IPMR. However, the resource duty of VoLTE calls is similar to the other VoIP applications or VoIP calls. Therefore, the traditional VoIP applications can benefit from the dedicated channel and header compression. From the measurements and analysis in this work, we find that CELT and Z.711 are two constant bitrate codecs, uh, and they are not that efficient. They are not network friendly either, as they consume more physical layer resource blocks. ESAC and IPMR are not resilient against noise, as Facebook Messenger and Viber exchange more traffic in the noisier contexts. However, most of the codecs consume less energy except Viber and Duo. Note that these applications with constant bitrate traffic do not react with noise or silence. The other applications actually react, and therefore such applications may expose the privacy of the speakers. As researchers have shown how the speaker's conversation pattern can be identified from the flow properties. Based on our analysis, we believe that the VoIP applications can benefit from context-aware codec selection. For example, a VoIP application can detect the surrounding noise or check better health prior making calls. Thank you very much for listening the presentation. And now I am ready to take your questions.